Hello everyone. So today let us discuss one very important concept from electricity and magnetism, that is electric potential. So in this class I'll try to explain the key concepts and some standard questions from this topic. Okay. So the first important term that you need to understand in this chapter is electric potential energy. So sir, what is electric potential energy? So electric potential is energy is nothing but interaction energy. So it is nothing but interaction energy between electric charges. Electric charges. So basically, the electric potential energy is nothing but the interaction energy that is present between the what? That is present between the electric charges. So, okay, we understood the definition, but now we need to understand what is the interaction energy and why this interaction energy is required and all this stuff, right? So, let me explain the concept here. Let's say, imagine there is only a single charge over here, okay, or else just imagine like this, there is a charge q1 over here and there is one more charge q2 over here. There are two charges like this. So obviously you know that this charge will apply a force on this one, okay, according to like coulomb's law of force. So by using coulomb's law of force you can tell that, so on this, if let's say imagine both the charges are positive, so they'll be repelled like this, right? And let's say like we are holding it or by means of some external force, so that means basically you can tell there is some interaction between these two charges, right? So that means someone would have created this system. So it's not like that, so the system from the start itself it will be like this, right? So let us try to understand how this system might have created. So I am just telling this way. Let's say there is a q1 charge which is already present. Okay, there is a q1 charge which is already present, and now you can see that there is no interaction. So in the entire universe, okay, like that means we'll call it as lab frame. Lab frame means in the universe which we are like analyzing. So let's say in the lab frame only q1 charge is there. In the lab frame only q1 charge is there. That means no interaction. Now I wanted to bring a charge and keep it at a distance of what? Let's say d. So that means, or how to perform this one? Imagine that initially the Q2 charge is at infinite. Initially the Q2 charge is at what? At infinite. Now from infinite, what will we do? We'll just bring this charge and we are going to place at whatever the position that I want. So from here, what will we do? We'll just bring this charge and then I'm going to keep it over here. Keep it at the point where it is, where we wanted to keep the charge. I'll keep it out there. Okay, so this is q2 charge. Let's say I wanted to keep this q2 charge at a distance d. So in this process you need to understand, let's say the q1 charge is already fixed. Why it should be fixed? Why? Because while it is coming, this q2 charge will apply force on q1 and similarly this q1 charge will apply the force on q2. So how we are bringing that charge from here to here, that doesn't matter. Okay, let's say in some random path we are bringing from the infinite to where? Infinite to a distance d. So that means you need to understand, while we are bringing this charge, obviously this q1 charge, it is already fixed. Okay, already I told this charge is what? Fixed. This charge is fixed and we are bringing this q2 charge from infinite to a distance d. So in this process we know that the q1 won't sit silent, right? So it will apply the force, okay, like coulombic force on the q2. So if both are positive, as I said, it's going to apply the repulsive force. It won't allow the charge to come near to it, right? It won't allow the charge, q2 charge, to come near it. So that means it's not an it won't go voluntarily from infinite to what? D distance. That means someone should have taken that particle or taken the charge from infinite to a distance what? D, right? So that means, so I am calling that as external force. Let's say externally by applying some force from infinite, we are taking this charge from here to here, right? Okay, that means, sir, how we are creating this system? We are creating this system. We are creating this system by the help of some external force. by help of some external force. So if I ask you like basically how many external forces are there here, then you need to tell two external force. What are the two external force? One is one is the force which is holding this q1 charge at that fixed point, and other one is the force that I am applying on q2 to bring from infinite to what, d. Then so here little bit of basics of work energy theorem is also required. Okay, so like basics, not like too much. I'm not going to go too much into the topic, but just basics are required. So even though there is a force acting on the q1 charge, the work done by that force will be zero. Work done by that force which is like ensuring that q1 will be at rest, that work done will be what, zero. So why that work done will be zero? Because displacement is zero, right? Even though force is there is no displacement for this q1 charge. As there is no displacement for this q1 charge, that means work done by this force F1, let me call it as F1, will be 0. And another external force is there on like Q2, right? But that is not 0. Why? Because for the Q2 charge we have the displacement. That means you need to understand that. So like already I told you, we are creating this system. Okay, we are creating this system, I forgot to write system, by the help of some external force. And obviously that external force is going to do some work. Sir, how we are like sure that it will do some work? Why? Because the q2 charge is getting what, the q2 charge is getting displaced. Yes sir, the force is there, displacement is there, and yeah, so there will be some work that will be associated by, or like the work that will be associated with the force that I have considered. So we will be doing some work, okay, by the help of the external agent. So and the next important point that we know, energy can neither be created nor be destroyed, right? Energy is one more important rule in physics, right? Energy is neither created nor destroyed. Neither created nor destroyed. So why we need to discuss this point, you will understand in a while. So energy is neither created nor destroyed. Okay, so you understood. And one important thing over here is, sir, how I am going to bring this charge from infinite to like this d distance, means I am going to bring the charge very slowly. Okay, we are going to bring the charge what? We are going to bring as we will bring the charge very slowly, no kinetic energy is involved. No kinetic energy is involved. That means no kinetic energy is there. Okay, as I already told earlier, so that means here when we are using the external force and there is some displacement, there will be some work associated, right? So now as there is no kinetic energy for q1 is at rest, and q2 they are telling they're slowly bringing this charge, right? When they're slowly bringing this charge, slowly means almost the velocity is zero. So that means both doesn't have any kinetic energy, but who is doing some work? External force is doing some work. So that means where that work has gone. So as I already told, energy can neither be created nor be destroyed, means now not be destroyed, right? That means energy cannot be like simply vanish. Okay, that means what happened to the energy, the work that I have done? So therefore the key important point here is the work that we have done, work done by the external force is stored as the interaction energy. So this is the reason, okay, we are having that interaction energy. Like as I said earlier, the system is not created, right, on its own. So like someone has to bring this q1 to q2 charge from infinite and create this type of system. So it can be like, later we'll see, this can be a ring, this can be a sphere, this can be a disc, this can be a rod, whatever it might be. Okay, it's not like that it will be like voluntarily formed, right? Someone should create it by bringing the charges together. So that means externally we are doing some work. Okay, then you need to understand that whatever the work that I have done externally, that energy cannot just vanish like this. That means, sir, what happened to that energy? That energy, you need to understand, is stored as the interaction energy between these electric charges, and that interaction energy only we are naming it as what? Electric potential energy. Okay, so I hope it's clear for everyone what is electric potential energy. Now let us try to derive what is the electric potential energy of what for two charges. So like there can be many charges, right? There can be many point charges, and like interaction of all these like what point charge, like there will be interaction between each and every like what set of point charges. Any 2 point charges you take, there will be interaction between them, right? Now I want to calculate a formula for electric potential energy of what two charges. So between two charges I wanted to find electric potential energy. So let us see how to derive this. Let's say, imagine there is a q1 charge which is fixed like this, okay, which is fixed. Now I'm trying to bring a q2 charge from infinite, right? When I'm moving this, I had to apply external force like this, right? And f external like this, because it will try to the charge will be repelled by this q1 charge, but I need to overcome that, so I'm applying external force left side, but electric force will be in what direction? This is force of repulsion. I'm writing force of repulsion, which is nothing but electric force, right? So this force of repulsion is nothing but electric force, and to overcome that I am applying the external force. And let's say at some instant the distance over here is what? D. At some instant the distance over here is what? D. So the distance over here is not D. Let us not fix it, because finally we need to bring it to a distance D, right? Or like let me take consider that at some instant the distance between them is what? X. Now slowly I am decreasing this distance and ensure that finally I will bring it to a distance what? D or some R or whatever it might be, but from infinite I am bringing. So now as I said, whatever the work done by the external force, that will be stored as what? That will be stored as interaction energy. That means simply we need to find what is the work done by the external force, right? What is the work done by the external force? But here the problem, sir, here a problem arises. Sir, what is the problem? We don't know what is the magnitude of electric force, right? Sir, what is the magnitude of external force that we are applying? We don't know, because they haven't mentioned it. But one thing, okay, one thing we know, that is for charge to move slowly, move slowly, no velocity should be gained, v equal to 0, which implies no acceleration should also be there. If acceleration is there, then simply the velocity will be like what? Increased. That means a net equal to 0, a net equal to 0, which implies if a, not a net, let call it as a. Acceleration of the particle is 0. Acceleration of particle is 0. Therefore what we can tell? F net equal to what? F net equal to 0. So therefore F net equal to 0 means the external force that I am giving is nothing but equal to what? The repulsion force that I will get from Coulomb's law. So what is the repulsive force that I will be getting from Coulomb's law? K q1 q2 by what? X square. That means, so I know the value of external force should be equal to what? The value of electrostatic repulsion force, that is Coulombic force, k q1 q2 by how much? X square. Now I wanted to find the work done due to the external force. Work done due to the external force. You know, whenever variable force is there, you can clearly see that it's a variable force. It's not a constant force. To write Fx like work done equal to what? Force into displacement. So as it is it's a variable force, so whenever variable force is there, I need to integrate it, right? So for small displacement dx, work done will be like what? Work done will be f dx, right? So for small displacement, work done will be what? F dx. So that means the total work done can be written as integration of all the small works, integral f external of what? F external dx. So what is that external force? Let me just write it over here. That external force is integration of k q1 q2 by k q1 q2 by x square dx, right? So 1 by x square integration will be what? X power of minus 2 plus 1 by minus 2 plus 1. You will get minus 1 by x. So therefore what will you get, sir? K q1 q2 is constant. As I said, 1 by x square integration you will get minus 1 by x, and limits are, initial limit is what? Infinite. Initial limit is what? Infinite. And final limit is what? Final limit is d. Final limit is what? D. right? So you can see that the final limit is d. Okay, d is the distance till where we need to bring it, and initial distance is what? Initially the separation between them is infinite. Now we need to understand that the external force, the repulsion force kq and q2 by r square is right side, and the external force is what? Left side. So and the displacement dx is also what? Left side. But here the value of dx, what is happening to the value of dx, can you guys tell? Dx value is decreasing, right? So that means dx value is actually negative. Okay, the dx value is what? Negative. So basically I just need to keep a negative sign over here, so ensuring that the work done should be the positive value, right? So how we are telling work done should be positive? Why? Because uh, the force is left side and displacement is also left side. That means the product should be what? Positive. F is a positive value, but you need to understand that dx is what? Dx is a negative value, right? So as I already know work done should be positive, so I shouldn't write f dx. What I should write? I should write minus f dx. So here also minus sign, minus will be there, minus minus will become what? Plus. So therefore the work done by the external force, work done by the external force will become how much? Work done by the external force will become k q1 q2 by d. So whatever this value that we have got, work done by external force, this will be stored as what? This will be stored as interaction energy between those two, and that only we'll call it as what? Potential energy. So therefore what will we say here? This is the, this energy will be stored as what? This energy is stored as potential energy in the system. Potential energy in the system. Whatever the energy that we got, the formula k q1 q2 by d. So this much amount of energy will be stored in what? This much amount of energy will be stored in the system of what? 2-point charges, right? So I hope it is clear for everyone, right? So this is the proof for this. Now let us discuss some like important points based on this. So let's say the electric potential energy of a system of charges, right? When multiple charges are there, what should be done? So you need to understand that this, as we know, energy is a scalar quantity. So we already know energy is what? Energy is a scalar quantity. So this is the first important thing you need to keep in mind. Energy is a scalar quantity, and then we also know between any two particles, between any two particles, interaction energy between any two particles, interaction energy I can simply write like this. So how we can write interaction energy? Interaction energy can be simply written as just now we got the formula, right? K q1 q2 by how much? D, where D is the distance between the charges, right? So we know the energy is a scalar quantity. We know energy is a scalar quantity, and between any two point charges, that's also very very important. Okay, so this formula we derived any particles means in the sense point charges. That's also very key point. The formula that we derived is for what? Only for point charges. Okay, and between any two point charges this interaction energy will be there. Now we need to see when system of charges are there, what will happen. So we'll have like different types here. First we can have discrete. Okay, discrete means individually there are like separate charges. For suppose there is a like what system of charges like this. So how many are there here? Basically how many charges are there? So you guys can see there are 5 charges: q1, q2, q3, q4, q5. So if I ask sir how many interactions will be there here, so as I said, between any two interactions, okay, between any two interactions like potential energy will be there. So therefore what is the formula here? You know, potential energy of the system, potential energy of the system, simply you can write it as sigma k qi by qi by qi by qj, where I is not equal to j, you need to take different numbers, because so like because of the same self charge you won't be having an interaction between two different charges, you will be having interaction kqi ij, and then by distance between the particles rij is the distance between the particles, and sigma of all these things you need to take. So keep the different values of I and j. So here I am keeping I shouldn't be equal to what? I shouldn't be equal to j. I shouldn't be equal to what? J. And you shouldn't take repetition also here. You shouldn't take repetition. Okay, I'm not keeping sigma value, so that you might be thinking, sir, here you will get 1 and 4, and again you will get 4 and 1. Okay, so if you're doing that way, then keep the sigma value running and divide it by 2, because every like both the interactions you will be getting, right? So q1 q4 and q4 q1, it is like same. So you do the entire thing and divide it by 2, that is also fine. Okay, so anyway, I'm not keeping any the value of from where to where I is running and j is running. Simply I'm just telling that you need to find interaction for each and every set of 2-point charges that we can consider. So that means, so if I take an n system of if I consider n system of particles, n system of discrete particles, then how many sets will be there, sir? So for n sets, for n charges, we will have how many interactions? We will have nc2 interactions. So nc2 means what? nc2 you already know, n into n minus 1 by what? 2. n into n minus 1 by 2 interactions will be there. That means in this case, if I ask how many interactions would have been there, how many interactions would have been there here? So the number of interactions that would have been there are 5 into 4 divided by 2. So that is 10 interactions. So here total 10 interactions will be there. You just need to add all those things to get the total potential energy of the system, okay, or like the total internal energy of the system, which is made up of like what? Discrete charges. Discrete means the charges are like separately they are arranged. Later we'll see what will happen. These charges are there continuously, like ring, okay, like for a disc, for a solid sphere, for a rod, for sheet. So you're going to see what will be the potential and how the potential works for those kind of continuous charge distribution. So here we are just seeing electrical energy, so electric potential energy of a what? System of charges. Now let us see some standard models based on this. So let's say here I am giving one question. So they'll give these kind of systems. They can give triangle, or they can give like rectangle, square, whatever it is, hexagon, and they'll ask you to find total interaction energy. So how to find total interaction energy? First let me find how many number of interactions will be there. Total how many charges are there? 4 charges are there. So therefore total number of interactions. So how many interactions will be there? Total number of interactions will be 4c2. 4c2 means nothing but what? 4 into 3 divided by 2, which is nothing but what? 6 interactions will be there. What are the 6 interactions? You know, q1 q2 q1 q3 q1 q4, that is 3 interactions. Forget about q1 now. q3 q4 q2 q3 q2 q4, that is 2 more, and then finally q3 q4. So as you can clearly see that the distance between the adjacent ones is what? 1. The distance between the adjacent ones is 1. So therefore from here total how many interactions must be there? 6 interactions. So therefore k, if I take common, k is same for everything, right? So k is nothing but the 1 by 4 pi epsilon naught value, where epsilon naught is the permittivity of free space. K multiplied by what will you get? q1 q2 by 1 plus q1 q4 by also what? q1 q4 by 1 plus q1 q3 by how much? Diagonal will be root 2. So with q1 all the 3 interactions are done. Next plus q2 q3 by what? q2 q3 by 1. q2 q3 is done, plus q2 q4 by its diagonal, so root 2, plus final interaction is what? q3 q4 by 1. So this will be the total interaction of the system. So like this, simply you can find interaction energy between each set, that is interaction energy between each pair, and then you can simply add them. Sir, why, how you can simply add them? Because already very clearly I have written an important note point here. Energy is a what? As energy is a scalar quantity, so there won't be any issue, there shouldn't be any issue in what, there shouldn't be any issue in adding them, as it's a scalar quantity. It's not a vector quantity like electric field, that I should be bothered about direction and all that stuff. Simply as it is a scalar quantity, I can simply add them. That's why I have written this point. Okay, and we know the interaction energy between each pair, that is kq and q2 by r, and we can find the net value and we can add it, right? So they can give triangle, they can give hexagon, they can give rectangle, they can give pentagon, whatever it is. Okay, next let us see one more question. Okay, so here again in this question you guys can easily find what is the interaction energy, right? So total how many interactions will be there? 3c2. Okay, 3c2 means simply how many will be there? 3 into 2 by 2, which is nothing but 3. Sir, what are these? q1 q2, q1 q3 and q2 q3. Only 3 interactions will be there, right? So simply I can find the interaction energy. So this value is what? 3 3, and this value is 4, so this will be what? 5, and this will be what? 5. So I can find the interaction energy. Sir, what is the interaction energy? But now here I am mixing this question with what? Work energy theorem, and let us try to create a question here. So let's say they are telling that these two charges are what? Fixed. These two charges are what? Fixed. These two charges are fixed. These two charges are fixed, and also I am telling that q1 equal to q2 equal to q. q1 equal to q2 equal to q, and q3 equal to q naught. So now first let me write the initial interaction energy. Sir, how to write the initial interaction energy? So this value will be there, as this is 3 and this is 4. This length will be what? 5. This length will be 5, and between these two it's 3 3, so it will be what? 6. So can you guys write what is the initial interaction energy? So let me write initial interaction energy. Initial interaction energy. Sir, what will be the initial interaction energy? Initial interaction energy is nothing but what? K I can take common. So between q1 and q2 is q, so q square by distance between them is what? 6, plus q naught by 5, plus the other one is also what? q naught by 5. So this is the initial interaction energy. Ui means initial interaction energy, and clearly they told that these two are what? These two are fixed, and they are like equal charges, right? That means q3 is kept what? Q3 is kept symmetrical. Q3 is kept, charge Q3 is kept symmetrical. So because of that, what will happen? As it is kept symmetrical, this can move like in what direction? Let's say, and Q3 is not Q naught. Let me take it as what? Negative charge, so that it will be attracted, right? Let me take it as what? Minus Q naught. So when you take minus Q naught over there, then obviously here when you write interaction energy, here minus will come, right? Yeah, so this is the initial interaction energy. So because of this negative, as this is a negative charge and Q naught value and Q are positive, I can also keep it as Q naught and I can tell Q naught, but here why I am writing minus Q naught means I am considering Q and Q naught are positive values. So as minus, then therefore minus Q naught will be a what? Negative value. So because of which the force here will be attractive, because of symmetry. This angle, if it is theta, this angle is also theta at any given instant. So that means as a result, this is going to move in what direction? The Q3 is going to move only in what? Vertical direction. So as I clearly told here, as Q3 is kept symmetrical, it will move only in what direction? It will move in, it just moves in it moves along y-axis. Now the question is, when the charge comes over here, then they are asking what will be the what will be the velocity. You might be thinking, sir, why the velocity like comes into picture over here. So you need to understand that when it is here, the interaction energy will be like some value, and when it is over here, then the interaction energy will be different, right? So let me write the final situation also. What will be the final situation? The charges will be something like this, right? Like this. This is Q, and this is minus Q naught, and this distance is 3, this distance is 3. right? Okay, sir. Then I can write the final interaction energy. Let me write UF. Sir, what will be the final interaction energy? Okay, this is an important model. Okay, so the final interaction energy is something like this. So what is the final interaction energy? The final interaction energy is k. K I can take outside, just like, and q square divided by what, 6, the same as the first thing, but now minus q naught by what, 3, and minus q naught by what, again 3. So you can see that initial energy is different from what, final energy. So that means, and that too you guys can see the value, what happened to the value, the value is increased or decreased. What happened to the value? So decreased, right? Because we are subtracting more value, so the value of potential energy is decreased. That means suddenly some of the value of interaction energy is like lost. But we know energy can neither be created nor be destroyed when there are no non-conservative forces, right? Here for time being there are no non-conservative forces. That means energy should be conserved, right? So let me find, like you can see that u initial is more than what, u final. So which implies some energy is what, some energy has lost, some energy has lost, which must convert into what, which must be converted into, which must be converted into, as it is having some motion, converted into kinetic energy, converted into kinetic energy of what, kinetic energy of the charge q3, kinetic energy of the charge q3, right? Because energy can neither be created nor be destroyed. Whatever the energy that system has lost, the interaction energy, that interaction energy should have stored as a form of what, should have stored as a form of kinetic energy. So therefore what is the conclusion here? The conclusion over here is, therefore ui minus uf equal to what, ui minus uf equal to half mv square. So this, from here you will be getting the answer. I am not doing the simplification part, okay, so that you guys can manage. So I am just going to explain the concept only. So I hope here it's pretty much clear for you. So from here you will get the answer, right? And one more thing I should be giving over here, mass should also be given, right? Let's say it got some mass 5 kgs, charge, it can be 5 kgs, right? Let us keep it as again meters are there, capital M, let me keep it as what, capital M. Then you guys can find, right? So basically they just asked us to find interaction energy, but I have just modified this question. And like on similar note, there will be one more standard question over here, okay? So that question also I wanted to explain over here. So I'll just give the question and I'll explain the concept, and I'm not going to do the calculation part. So one more important model here could be, they can tell there is a charge like plus q and minus q charge is there, and they'll give this mass is, let's say m, and let's say this mass is 2m. So randomly I'm just giving some values over here. So q minus q, this will be attracted. Let's say initially the distance between them is d, initially the distance between them is what, d. Now what they'll be asking is, they'll be asking what will be the velocities, okay? Like if both are moving, then it will be a good question. Then you need to do momentum conservation as well as what, energy conservation. When one is fixed, then you cannot apply momentum conservation. So why? Because like we are applying an external force on one charge to get fixed, right? So that's very very important. If both are moving, then it's a good question, okay? It will be little complex, you need to write 2 equations. If only one is moving, it's very easy for you, okay? So anyway, I'll explain both the models. So you never know, like any of these models can be asked. So first model 1, in model 1 q is fixed, q is what, fixed. In model 2 both are free, both are what, both are free to move. Like in both the cases there is a difference, okay? So what is the difference? In this case, in the first case, what will happen, you know? First case, simply like only mass m2 will move. So that means I am just drawing the diagram over here. So it will be something like this. Mass 2m will move, this q is not going to move. So therefore like interaction energies I can write, no, u initial, u final, and only, as I said, only this 2m mass is going to move, which is negative charge, let's say with some velocity what, with some velocity v. So therefore whatever the kinetic energy that we should get, half 2m into v square, from where you will be getting, from we will be getting delta u, not delta u, finally it will be decreased. So delta means always final minus initial, no, final it will be decreased. So better I'll write u lost, that means potential energy lost. Whatever the lost potential energy is there, that will be converted into what, the kinetic energy of this particle, the kinetic energy of this particle alone. And this won't be having any kinetic energy, as you can clearly see that this is what, fixed. Q charge is what, fixed over here. Okay sir, fine. In the second case, what will happen, sir? What is this u lost? U lost, you guys know, you just need to find initial interaction energy and final interaction energy. After finding initial interaction energy and final interaction energy, you just need to do the subtraction from there, and you're going to get the what, like loss in potential energy. And from there, once you get the loss in potential energy, equate that to what, the gain in kinetic energy of this 2m particle, and you're going to get the velocity. But in the second case, when both are free, the situation will be something like this. When both are free, see here, when both are free, then like we are going to get some, both the charges will get some velocity, let's say v1 and v2. So you guys need to understand, the net force on the system is what, 0. Earlier net force on the system is not 0. Okay, earlier, I'm just writing the point over here, earlier net force is not equal to 0. Why? Because this is like, here some external force is there to fix the charge q. But in this case f net on the system, f net. So you might be thinking, sir, this is getting attracted, this is getting attracted. Yeah, both are getting attracted, but you know, according to Newton's third law, it's an action and reaction, right? So the net force on the system, this will apply on plus q charge in this way, this will apply on minus q charge in this way. The net force will become what, 0. As the net force on the system is 0, we can conserve momentum of the system. Net force on the individual particle is not 0, net force on the system is 0. As net force on the system is 0, I can conserve what, momentum. Initial momentum is what, 0, then final momentum should also be 0. So for the final momentum to be 0, this will have positive momentum because it's moving right side, and this will have negative momentum because it is moving what, left side. So therefore I'll write mv1 equal to what, mv1 equal to 2mv2. This is one equation I got. But we have two unknowns, right? What are the two unknowns? I have v1 and v2 both as what, unknowns. So we have two unknowns and we got one equation. We have second equation also, right? Energy conservation. Whatever the energy that is lost, that energy should have been stored as what, kinetic energy of both the particles now. That means this, whatever the equation that I have written, this is the first equation, and second equation that I should be writing here is what, this is momentum conservation. Okay, this equation is nothing but what, momentum conservation. Next, energy should also be conserved. Energy can neither be created nor be destroyed, right? Because there are no non-conservative forces over here. So therefore, the u lost, whatever the lost energy must be there, it should be gained as what, kinetic energy of both the particles. So that is half m into v square, half into second mass 2m into what, v2 square, right? So, and this is our equation number 2. So you guys can clearly see that I have two variables and I have two equations. From here I can solve and I can get the answer, right? So like, these are some important models based on the interaction energy between like what, 2 point charges. Okay, so I hope like all these three questions are clear for you. So let us move on to the next concept. So the next concept is what, sir? The next concept is like, if I want to discuss, you can discuss more models over here. Okay, like the shortest distance of approach and all those things, but I'll try to make a different video because then it will become very long. Okay, so this video I'll try to take only 1-2 examples like for every concept, and I'll move on, and then I'll keep a separate video for problem solving for different levels. Okay, for mains and NEET level 1 video, and then for advanced another video, and for like Pathfinder and Irido we'll make some different videos for like different level of questions, so that when I segregate that manner, so whatever the level that you want, you can go and you can check that, right? So yes, so it's clear. So then let us move on to an important concept here, that is what, electric potential. This is our next concept. So electric potential, so in simple words, electric potential is nothing but it is also an interaction energy, but I can tell what we can tell. So it has a multiple definition. I write one definition over here: work done work done by external force, work done by external force in bringing a unit positive charge. Unit positive charge are also called as test charge. Unit positive charge are also called as what? Test charge. Unit positive charge or test charge from infinity to infinite distance or long distance, from infinite distance or long distance to a specific point, to a specific point, to a specific point where we need the potential. Okay, in simple words, this is one definition I can tell. Electric potential is nothing but work done by the external force in bringing an unit positive charge from infinite distance to a specific point. Okay, that means already I have found what is the work done in bringing a like what, like some random charge q2, right? Now if that instead of that q2, if I take just q1 charge, that means in other words simply I can also write this one in a different way. It's nothing but energy per what, per unit charge. So potential can simply given as what, interaction energy per unit charge. Potential in simple words can be given as what, potential is interaction energy on a unit charge, on a unit charge. That means we just need to divide with the charge, right? So therefore v simply I can write it as what, potential energy u. Symbol for potential is v and u is the symbol for potential energy. U by q, whatever the q that I have taken. So this is the formula. But here there will be a misconception. Okay, with the students I wanted to clear that misconception over here. When I say sir potential is u by q, then you might be thinking sir, like in the previous question, let's say I am taking up this question, you might be thinking sir, I have found the u, sir u like in total interaction energy I have found, sir this total interaction energy divided by like what charge we have to take, sir. Let's say I wanted to find potential over here, so this energy divided by q1 will give the potential. No, it's wrong. Okay, so you need to understand that. So here like at what point you need to find the interaction, there you need to keep a what, point charge. For suppose if you want to find what is the potential over here, what you need to do, like you need to find the potential only that is associated with the interaction energy that is associated with only q1, right? Because there is nothing to like do with what, q2 and q3, like for like to bring an unit positive charge from infinite to this point. So already I am bothered about what, interaction between q like this q1 and q2 and q1 and q3, right? So why to bother about the interaction energy of like what, q2 and q3, they are like already arranged over there. So if I want to find the potential at this point, you shouldn't find the total interaction energy and divide by this charge q. Okay, it's just like a basic point. It might not be required in solving questions, but you need to have that clarity that if I want to find the potential somewhere, okay, so it's like I need to just find interaction energy due to what, interaction due to each point charge separately. I won't be taking interaction due to the other charges. I won't bother. Like previous case, sorry, n charges are there, nc2 interactions will be there. No, to find the potential I am not bothered about all those things. Okay, I'm not bothered about all the remaining things. Okay, so I hope it's clear for you guys. Okay, yeah, fine. Then next, so from here we understood that okay, potential is nothing but potential energy per what, per unit charge. That means for suppose I'm just giving an example over here. Let's say there is a system like this, like previous I'll just take 5 charges randomly like this. Let's say q1, q2, q3, q4, q5, like this. So when u is a scalar and q is a scalar, so you need to understand that potential is also a what, scalar term. And let's say I wanted to find the potential due to all these charges at this point p, then simply what you need to do, you just need to find the potential or the interaction energy. Sir, how to find the potential over here? As I said, at whatever the point you need to find the potential, no, there you just keep a 1 coulomb charge, unit charge. Okay, 1 coulomb is nothing but what? Unit charge. So I kept a unit charge and I'll try to find the interaction energy over here. Simply I'll find interaction energy over here, or else before this let me just derive so anyway, okay, instead of explaining this, anyway you know potential is a scalar, you can just add it up. Instead of this I'll just give a note point. This very very important point, that is potential due to a unit like point charge. Potential due to point charge. Potential due to a point charge at a distance r. Sir, what is the potential due to a point charge at a distance r? Let us find it. Sir, how to find this? Imagine there is a q charge. I wanted to find what is the potential at this point P, which is at a distance of what? Which is at a distance of r. So how to find? Already I told you, you just need to keep a 1 coulomb charge, right? 1 coulomb charge, unit charge. 1 coulomb unit charge, I have kept it over here, unit charge. And the interaction energy U is nothing but what? Simply. So therefore, the potential V is nothing but interaction energy between this QA into K. Interaction energy already we have seen, no, for point charges. K Q1 Q2 by what? K Q1 Q2 by R. So that is K Q1 Q2 by what? R. So that means, therefore the formula for potential due to a point charge at a distance R is given as what? KQ by R. The potential due to a point charge at a distance R is given as what? KQ by R. So now I am going to give some important points that you need to keep in mind regarding this. One second. Let me move it to somewhere over here. Yeah. So now I'll give some important points here that you guys need to remember. So the points regarding potential, the important points regarding potential are: first point, it is a scalar quantity. It is a scalar quantity. So therefore no need of bothering about directions and all that stuff. Just like energy, whenever you want to like add, simply you guys can add. Okay, so that's the first point. And the next second point that you need to understand is, so one more important point, this is the reference that I will be taking. So the potential at infinity is considered as what? Considered as zero. That means this is very very important. Potential at infinite, in general, if they want to create any hypothetical question they can create, but in general we'll assume that the potential at infinite, okay, as zero. Why? Because when the charges are like separated for like by infinite distance, there won't be any interaction, right? So there won't be any interaction. Obviously, if there is no interaction energy, so if there is no U, okay, then there won't be obviously potential also. So that's why this is our reference that I will be taking. Okay, so that's one more important point. And the next important point is, you need to understand that potential decreases. Okay, potential decreases in the direction of electric field. Very 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 important point. In the direction of what? E bar. In the direction of E bar. Potential will decrease in the direction of electric field, or else there is an alternative definition also for this. What is the alternative definition? You know, electric field lines will flow from higher to lower potential. From higher to lower potential. Electric field lines can only flow from where to where? Higher potential to lower potential. So this is one more important point. Okay, so these points are like, for time being, these points are sufficient like to tackle the examples that I am telling. So next, let us try to discuss about potential due to a system of what? Potential due to a system of charges. Potential due to a what? System of charges. For time being, I'll just create one simple question, and from there, let us go to a continuous charge distribution. Again, as I said, like earlier, I told interaction energy between like what? Discrete charges, but continuous charge system I haven't told, right? Now we'll discuss the potential over here, and then we'll discuss the potential for continuous mass distribution, and then we can automatically discuss what? Interaction energy, that is potential energy for like what? Continuous charge distribution also. So potential due to what? System of charges. So already we have derived a formula for what is the potential due to point charge. Okay, potential due to a point charge, that is kq by r, and we have told it's a scalar quantity. First I'll take what systems? Discrete system. So through some questions I'll try to explain. So I'll give a simple question which I have already taken up. So let's say imagine there's a square like this. Imagine there's a square, and like here we are having q charge, total how many charges are there? 3 charges, q. Okay, and like this, at this point, let's say this vertices, they are naming it as O, this vertices is O, so they are asking find the potential at O, and they have given all the distances are 1 meter. Side length is what? 1 meter. Side length is given as 1 meter, 1 meter, 1 meter. So now the like thing is we need to find the potential at O. So potential at O, let's say, potential at O can be simply given as what? Scalar sum of, anyway it's the scalar, right? Scalar sum of potential due to each charge. Okay, scalar sum due to what? Scalar sum of potential due to each charge. That means, so therefore potential at O, O is simply nothing but what? Kq by 1 for one charge, and for another charge also kq by 1, but for another charge it is a diagonal point, opposite diagonal, so kq by what? Root 2. So therefore which is nothing but kq, if I take common, we will be getting 1 plus 1, 2 plus 1 by root 2, 2 plus 1 by root 2. So this is the potential. Okay, so like this, finding potential due to the discrete charge system, it won't be a task for us. It won't be a big task for us. Easily you guys can find what is the potential due to what? What is the potential due to a discrete charge system. Okay, so if this is clear, then next, as I said, continuous mass distribution you need to take, right? Let us take continuous. Second case is what? Continuous charge distribution. So here there are some standard cases that we need to take in this continuous charge distribution. Only standard things. Okay, so first let me take a case. Let me take it as a ring. There is a ring which is, let's say, carrying a charge q. There is a, let's say, ring which is carrying a charge q, and radius of what? Radius of the ring is, let's say, radius is r. Radius is r. Now I wanted to find what is the potential at the center. To find the potential at center. To find the potential at center, first let us find the potential at center, then let us go for the 3D thing. Okay, so first let me find the potential at center. Let us take the ring like this, which is having a charge q, and the ring radius is given as what? R. So, but you need to understand that till now we have learned only the formula for what? Potential due to, till now we have learned the formula for due to what? Potential due to a point charge only, right? We haven't learned potential due to any continuous charge distributions. Then sir, how to approach for this one? Simple. So as whatever the formulas that we know, those formulas only we'll use. I already know the potential due to what, like point charge. So what I'll be doing, so here I'll go here, like I'll consider an d theta angle, small angle here. What, how much angle? Here I'll consider a d theta angle, and small patch I will take here. So the small patch, it can be taken as what, dq, small charge. And so due to this dq charge I can find the potential over here. Then what will be the small potential dv? Okay, small potential dv is the small potential due to this point charge. dv means small potential, which is nothing but k into what is the small charge, dq, small charge dq, by what, the distance of this point, distance of the point. I am finding potential at the center. Okay, potential, the first point where I am finding at the center, I am finding first one, I am finding at the center. So then kq by, for like it is at a distance, this point is at a distance of what, radius r. So now integrating on both the sides, as r is constant, so therefore simply I'll get v equal to what, kq by r. So simply you need to understand that as all, like for all the dq charges, the center is at a equal distance r. So simply whatever the charge of the ring is there, okay, so by using that charge, due to each and every point charge, the distance is like what, same, which is r. Directly the formula will be what, kq by r, because for each and every like dq charge, it is at same distance. If the distance is varying, then it would have been a different task, right? But as the distance is fixed, simply the total potential can be simply written as what, kq by r. Now instead of taking at center, let me take some axial point. Let us take some axial point. So how to find the axial point? So here also it's very simple. So because the distance, let's say axial point, I need to find at a distance x. You need to understand that from this axial point P, the distance for the rim, okay, I'll call it as like rim, each and every point of the rim is what, same. It's a 3D shape that you need to understand. There is a ring like this, and here there is a point. Due to that point, each and every like what's the distance to the circumference of the ring will remains what, same. So and what will be the distance? Simply it will be, what is the distance over here, root of r square plus x square. As the distance again it is same, simply therefore potential on the axis, and here the potential at the center. The previous formula is what, potential on the center, and the potential on the axis. What is the formula you will be getting? Simply kq by root of what, kq by root of r square plus x square. Okay, kq by root of r square plus x square. Actually here there is an important thing later. Okay, so after some time we'll learn a relation between what, electric field and potential, relation between electric field and potential. If I take this potential and use that relation, I can also find what is the electric field due to an like ring on its axis, which already the formula, kqx by r square plus x square whole power of 3 by 2. So you guys can get it from here, after knowing the relation between what, electric field and potential. So this is the first standard charge distribution that you need to know in continuous charge distribution. And the second one, let me take one more standard one, that is, so in the continuous charge distribution B, let me take a rod over here. Okay, rod. So due to rod or a linear charge distribution, let us try to find the potential. So imagine there is a rod like this, and I wanted to find potential due to this at a distance d, and let's say charge is q and length is l. Now how to approach for this one? Again we don't have any direct formula for this, right? So I'll be just breaking it up. Okay, rod also there is two cases. One is like this is axial, another one is what, equatorial. So there are like again two cases. So I'll just tell how to approach for these two cases. So again we have two cases over here. So I'll go to a distance x, and here I'll consider a small thickness. So what will be the small thickness, dx, and due to this dx charge, okay, dx charge will carry how much charge, dq charge. So due to this I can write the small potential dv. So what is the small potential dv? Small potential dv is nothing but small charge dq divided by, it is at what distance, x. Here I cannot write, simply I'll write kq by d, I'll write, no, this d, the distance for each and every like point charge that we'll take is varying. So like the previous case, we cannot directly write the answer over here, so I cannot simply integrate, and I cannot take k and x outside, because x is also what, variable. So that means first let me write the dq charge. So how to write dq charge? So already k by x, dq charge can be written like this: charge per unit length multiplied by what, length. So for uniform case, okay, it should be given, it is a what, uniform distributed, like uniformly charged rod. Then the charge density will be given as what, q by l, and length of that part is what, dx. So therefore this will be the small charge dq. Now I will integrate. Now you guys can see that kq by l is constant, I can take, but x I cannot take outside, right? Now when I integrate on both the sides, integral dv, so I can take kq by l outside, but x I cannot take outside, 1 by x dx. Now I'll integrate on both the sides. So integral dv is nothing but what, simply integral dv is nothing but rod. Again here what I am taking, which point I am taking, axial point I am taking. Again equatorial will be there. So therefore here integral dv is nothing but what, v potential, and kq by l, integral 1 by x dx is nothing but what, you guys know, ln x. And limits are from where to where, initial limit is d and final limit, this is the initial limit, x distance. Charge is there from what distance to what distance, it's not from 0 to d or 0 to l or 0 to d plus l. Charge is there from here to here only, because you can take charges, you can take point charges only from this point to this point. That means from a distance d to where, from a distance d to, you can take till d plus l. So log a minus log b, log a by b will be getting, so ln a by b. So therefore potential in this case, the formula will be what, kq by l into what, ln of d plus l divided by how much, d plus l divided by d. So this is the potential due to a rod on its axial line, potential due to a rod on its axial line, right? So I hope it's clear for you. So now as I said, there is one more case, right? So what is another case that we can take? Another case that we can take up is equatorial, right? Equatorial point. Sir, what is equatorial point? So let's say we have like this. Now I need to find what is the potential at a distance of what, at a distance of, let's say, y from the center, or let's say a distance of d from the center. Okay, so this I am not going to derive, so I am just giving it as a homework that you guys can like solve. This is also q charge and length l. So now what I will be doing, so I will go to a distance of what, but this is a little tricky one, and it's a nice one also. These type of integrations will be regularly coming in our upcoming topics, like in magnetism, in current electricity, later in wave optics. Okay, so everywhere these type of like integrations will come in first year mechanics also, right? So you need to understand these things. So I'm just giving it as a homework, you guys just try it out. Let's say it's theta. Now I'll go to a small angle d theta. This is d theta. I'll take a small element over here. What is this element length? That is a tricky part to find. This is our small element dq charge. You take this dq charge and then like write the small potential due to this, that is, so if you know this distance d, you can find this r, right? So what will be this r? So cos theta is nothing but what, cos theta is nothing but d by r. So therefore r is nothing but what, d by cos theta. Now what will be the small potential dv? Sir, small potential dv is nothing but k into small charge dq, k into small charge dq, by it is at what distance, r distance. R is nothing but what, d by cos theta. So d is constant by cos theta, cos theta will go to numerator, d by what, cos theta. So therefore dv, what will you get, dv you will be getting k into dq into cos theta by dq into cos theta by d. Okay, so now the important task is to finding this dq charge. This dq charge, how to find this dq charge? So like this dq charge can be found, charge per unit length is what, q by l. Now you need to find this distance. Okay, so anyway I'll be just discussing this because it's very 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 important in your future like what concepts as well. So that's why I'll try to derive it over here, because that method is important, not the formula. Okay, the method that I'll be using to derive is important. So here this distance, actually this distance will be equal to r d theta. Whatever this distance is there, that will be r d theta, but I need to find this length, right? So that whatever this figure over here is there, I'm just zooming it up. So this is the horizontal line, and this is over here, and here I'm drawing a perpendicular. Here I am drawing a what? Perpendicular. And you need to understand that if this is theta, this will be 90 minus theta, and this angle will be theta. Which angle will be theta? This angle will be theta. Let me draw it a little more big. So this is the dq charge length, and this is our extension, and this is the perpendicular. And as I said, this is the dx length, and this is r d theta length, and this is our theta. So basically now I need to find this dx length in terms of what? R d theta. So how to find? So again I can write cos theta from here. Whatever the diagram that is there, from here I can write cos theta. So what is this diagram? You understood? No, this part whatever that is there, this one I zoomed over here. So therefore cos theta is nothing but what? Cos theta is nothing but adjacent side r d theta by what? Dx. R d theta by dx. So therefore dx equal to what? Dx equal to r d theta by cos theta. So I got dx. So once you get dx, so then dq is very simple. So how to write dq? dq is nothing but q by l, charge per unit length. K by d is there, and k by d is constant, and dq is nothing but what? Charge per unit length, q by l, and the distance dx is nothing but what? R d theta by how much? R d theta by cos theta into what is there? Cos theta is there. So then theta cos theta will get cancelled. So therefore here one second, r is variable, right? Okay, I would have kept it as r itself. Okay, fine. Again, r is a variable thing. R already I found, it's nothing but what? D by cos theta. So therefore what will you get? dv equal to k q, or else from here you can see r by d. What is r by d? R by d is nothing but what? 1 by cos theta. 1 by cos theta is nothing but what? Secant theta. So kq by l secant theta d theta. So now I should integrate on both the sides, and I should keep the limits from theta running from minus theta naught to plus theta naught. What is the theta naught value? You guys can substitute, and from here you can get the answer. Okay, so I hope it is pretty much clear for you. And similarly you guys can like find it for ring also. Okay, you guys can find it for what? Ring. Sorry, not ring. Ring already I have found. So the C is for what? The standard case C is for disk. Standard case the final one is for what? Disk. Sir, disk, how to consider for the disk? You need to understand disk. The elements that I will be taking is what? Q and radius R. So as it is a disk, you need to understand that so it will be filled. So earlier it is like only linear charge density will be there, lambda, but now here what will be there? Sigma will be there, because it's an aerial object now. So earlier it's a linear object, now it's like what? Aerial object. So now like this we will be having what? Sigma now. So I can give Q and R or sigma and R. Okay sir, that we understood. So then here how to consider, so already I found the potential due to what? Potential due to rings. So how to find, so let's say here I want to find what is the potential at a distance, let's say x. What I'll do, I'll go to a smaller distance, and I'll consider a ring. Which is of what thickness, I'll consider a ring of thickness dr. What? dr. Now I know how to write the value of this dq. So how to write the value of this dq? As I said, dq, small dq can be written as sigma. Sigma is the surface charge density into like area of this one. So what will be the area of this one? If I cut this, whatever this part is there, if I cut this, if I just arrange it in this way, so it will be forming what? It will be forming a rectangle. So actually it's like a curved one, so it will be a circular track. But what is the length of the circular track? Length of the circular track is 2 pi r, and width is what? dr. So when you cut it and if you just make it straight, it will be forming a rectangular strip of length 2 pi r and breadth what? Of length 2 pi r and breadth dr. So therefore sigma into what is the area? As I have said, area is what? 2 pi r into what? dr. But how to write the value of sigma, sir? Sigma is nothing but surface charge density, right? That is charge divided by area. What is the area? If it is uniformly distributed, it will be what? Pi r square into 2 pi r what? dr, 2 pi r dr. So from here, like pi will get cancelled, and then from here I got the dq value. Dq value is how much? K 2r dr, k 2r dr by what? R square. So I got the value of dq. So already I found the what is the formula for what? The formula for the potential due to a ring. Formula for potential due to a ring at a distance what? X. Basically, let's say I wanted to find what is the potential at a distance. Let me take which ink? Blue ink. Let's say I wanted to find potential which is at a distance of what? X at this point P. So therefore dV. So I found the value of dq. And from here small potential dV is nothing but small potential. Why I am telling? I am not finding due to the entire thing. I am just finding the potential due to only the small ring. That's why it's not the entire potential, it is small potential dV, which is nothing but k into the small charge dq by distance. It is at what distance, for the ring? Already we have seen the formula, no? Under root of what? R square plus x square. But you guys need to understand that here what is variable? X is a fixed value, but R is variable. And then again substitute this dq value over here. So that is k into dq. How much you are going to get? 2qr dr by capital R square into root small r square plus what? X square. Correct one, so dq are replaced with k by this is there, and this is 2qr dr by r square. Yeah, fine. So then now I'll integrate on both the sides, and so therefore v on the axial line due to a disk will be equal to what, sir? Limits from where to where I'll keep? Smaller limits 0 to capital R, because the ring should be considered from where, what radius to what radius? 0 to capital R radius. When you substitute this, so I am just directly writing the formula sigma, where sigma is the what? Surface charge density. Sigma by 2 epsilon naught into root of x square plus r square minus x. So this is the formula that you need to remember. So anyway, I have told the complete derivation. You just need to integrate and keep the limits, and you will get the final answer. So this is the potential due to what? This is the potential due to disk on its axial point. Okay, so I hope it is pretty much clear for you. So if you know the potentials, like potential due to the standard cases should be known. That is like for ring, for a point charge, for a ring, for a rod on axial, for a disc on axial, for rod on equatorial point. So it will be very good, it will be very beneficial if you remember all these formulas. Why? Because the same whatever the previous questions I have explained over here based on the like energy conservations, now the same questions earlier we have done with what? Discrete charges. Now the same questions can be replicated with what? The same models of questions can be given with what? This continuous charge distribution. So how? See, I'll just create one question over here, just a simple question, so that you will get an idea. So that's why you need to understand the concept very clearly, and then they can connect these concepts however they want. They can connect these concepts, right? For example, let's say here I'm just creating a question. So what is the question? I consider a ring of charge q and radius r. From the center I am telling that I am keeping a negative charge minus q at a distance of what? The ring is fixed. The ring is what? Fixed ring. Okay, if the ring is moved, then again this concept also I have told. Basically I am like whatever the concepts I told, you need to understand. Even though if the ring is moving, then this center of mass of the ring will get some velocity, this will get some velocity, and when both the charges are not fixed, already I told that model, right? That concept you need to follow. So let's say it is fixed, then and also it is kept at a distance r. Now they will be asking initially, let's say it started from rest, they'll tell initially it started from rest, and mass of this one will be given as what? M. M. Now they will be asking you to find what is the velocity of this after reaching the center. What is the velocity of this particle after reaching what? Center. So how to find? Simple. So already I told you initial interaction energy, let us find. So what is initial interaction energy? So minus, why? Because one is having minus, because one of the things is carrying negative charge. So q, that is kq square by distance. When this is r and this is also r, so what will you get? Root 2r. So this is the initial interaction energy. This is the initial interaction energy. Root 2, not r is outside, right? So root 2 times r. Then u final, what will be u final? U final is nothing but when it comes to the center. When it comes to the center, finally kq square by what will you get? It will be at a distance of what? R. So tell me the value is decreased or increased. So you can see that, forget about the minus, the denominator has what? Decreased. That means value would have increased magnitude, but negative is there, so that means value, total value is decreased. That means u lost can be written as what? U initial minus u final. U initial minus u final. So from here what I can take common? I can take common kq square by r if I take common. Kq square by r if I take common. Initial minus final, minus of minus will become plus, so 1 minus you will get 1 by root 2. 1 minus 1 by root 2 you will be getting. So this will be u lost, and so like I'll equate this u lost to what? So whatever this lost and then final point, I know whatever this lost interaction energy is there, potential energy, this entire energy will be converted into what? Kinetic energy. And from there you guys can find the velocity, right? You can find velocity of this point charge, whatever the velocity of this point charge that is there. So like this they can ask many models. They can keep 2 rings over here. Okay, 2 rings. Okay, rings, it will be difficult. They, like by keeping the rings they might ask interaction energy, so that I am leaving up to you. So if you want, you guys can like try. So it's difficult, like maybe you need to do the integration part, which will be like very lengthy. Yeah. So I hope, like as I said, whatever the models that we have discussed for discrete models, discrete charges, now the same similar models they can also ask for what? They can also ask for continuous mass charge distribution also. And they can also give some questions where variable charge density will be there. So those type of questions, okay, we'll cover it up in what? Problem solving sessions. Now it's just all about like explaining theory and like some like 1 2 like standard examples or like models based on that concept, so that you'll understand it better. But as I said, for problem solving strategies, we'll come up with different videos where we'll tackling different models, basically the previous year questions, whatever the questions that they have asked in previous entrance exams, and all those things we'll take up, and there we'll try to learn. So basically I try to cover up the theory of the potential here. So next class will be on the relation between electric field and potentials, which is very 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 important in the exam point of view, competitive exam point of view. And the other concept that I'm going to discuss in that class, that is also very very important. So actually I could continue in this class, but it's already becoming so a lengthy one. So it's already almost 1.5 hour, 1 hour 20 minutes. So I'll try to keep it in a different video, that is relation between electric field and potential, which is very very important for competitive exams. And the second one is dipole. Okay, so these two are the concepts that are left out in this electric potential concept. So the next video I'll try to cover up that, and then the theory part is over. Then so problem solving will be done in a different video, so which you guys can go through. As I said, in different levels will be done. Okay, so I hope it's clear for you. Once again, just go through all the key points, note points that I've told, and try to understand each and every point. So as I already told in last classes also, that quality is more important than what? Quantity. Ensure in understanding the concepts very clearly, so that in competitive exams, obviously they'll create a new model, but the standards and basics will be same. So your preparation should be in such a way that you should be able to tackle any new question or new model that they have given, right? So that will be happening only when you are trying to analyze the situations that has been given in your classes. You need to analyze the situation on your own, then only you will be able to replicate this thing in final exam, like in the competitive exams. Then only you can perform well in the exams. Otherwise, if you're just focusing on doing more and more questions without knowing how those equations has come, so or without having the complete conceptual clarity, so just by mugging up the formulas and mugging up some different cases, mugging up is fine. for sure you need to, for competitive exams it's not an like what descriptive exam, like you need to do proofs and all, right? So competitive exam it's like time bounded thing, so you need to remember many things, but the mugging up thing or the remembering thing should be like what that should be done in an intelligent way. That means, so obviously they are not going to give like all the standard questions directly from the standard books and all. They're going to do a small change. And so like even when they've given the small changes, when they do the small changes in the question, you will be able to solve only when you have a conceptual clarity on that concept, right? So that's why I try to analyze each and every situation, like that is there, that will be there in the solved examples. You can take HC Verma or DC Pandey or Sengesh, or even your class notes, whatever like your teacher will be teaching. Try to analyze each and every situation that is given. Okay. Okay then, fine, thank you, bye bye.